This section examines basic principles of light vehicle suspension systems. The suspension system isolates the body from road shocks and vibrations, which would otherwise be transferred to the passengers and load. It also must keep the tyres in contact with the road. When a tyre hits an obstruction, there is a reaction force. The size of this reaction force depends on the unsprung mass at each wheel assembly. The sprung mass is that part of the vehicle supported by the springs, such as the body, the frame, the engine, and associated parts. Unsprung mass includes the components that follow the road contours, such as wheels, tyres, brake assemblies, and any part of the steering and suspension not supported by the springs. Vehicle ride and handling can be improved by keeping unsprung mass as low as possible. When large and heavy wheel assemblies encounter a bump or pothole, they experience a larger reaction force, sometimes large enough to make the tyre lose contact with the road surface. Wheel and brake units that are small and light follow road contours without a large effect on the rest of the vehicle. At the same time, a suspension system must be strong enough to withstand loads imposed by vehicle mass during cornering, accelerating, braking, and uneven road surfaces. Applying a force to this object deforms it. Removing the force lets it return to its original shape. This characteristic is called elasticity. Automotive suspension systems generally use the elastic properties of metals to provide the springing medium. The springs are located between the frame and the axle assemblies and are shaped to suit the application. Leaf springs are normally semi-elliptical, and they absorb the applied force by flattening out under load. Coil springs are formed in a spiral from a single steel rod and absorb the force of impact by twisting. Torsion bars are held rigid at one end and twist around their center as the suspension arm is deflected. They all return to their original shape when the deflecting force is removed. Non-metallic materials like rubber can provide the main springing action, but are more commonly used as stops to limit extreme suspension movement. The stops can also be shaped to provide an auxiliary springing function. In light vehicle applications, air is normally used only for ride height control. When a vehicle strikes an uneven surface, the springs are deformed from their original shape. They return to their original position but tend to overshoot and set up oscillations. This makes the vehicle bounce up and down, which makes the ride uncomfortable. It can produce forces that make the tyres bounce, and a bouncing tyre won't grip the road surface well. Shock absorbers have a marked effect on how well tyres follow a road surface. They damp the natural bounce over the road and reduce spring oscillations. There are different kinds of shock absorbers, but they all use a piston sliding in a cylinder filled with oil. The dampening action occurs as a result of the piston movement, forcing the oil through valves in the piston and at the foot of the shock absorber, which restrict oil flow. The oil heats up from this continuous movement as the energy of motion of the suspension is transformed into heat. This heat is transferred through the body of the shock absorber to the outside air. This section examines the solid axle or beam axle. The solid or beam axle provides a simple means of locating and mounting the hub and wheel units. Together with leaf springs, it forms an effective non-independent suspension system. Similarly with coil springs. It is still used in the rear suspension of many front-engine rear-wheel drive cars and light commercial vehicles, and as the front suspension on many heavy commercial vehicles. On rear-wheel drive vehicles with leaf springs, the axle housing is held in place by the springs and no other form of location is needed. The drive is transmitted through the final drive unit and axles to the wheels, and therefore the axle is referred to as a live axle. When a vehicle accelerates from rest, the resistance of its mass causes a torque reaction, producing a tendency for the axle housing to rotate in the direction that is opposite to wheel rotation. A similar effect occurs during braking, but with the twisting effect in the direction of wheel rotation. In both cases, this tendency can cause leaf spring wind-up, and the twisting action can interfere with suspension motion. It is usually controlled by mounting the axle housing closer to the fixed shackle point, so that the spring's front section is shorter than the rear section. The short, stiff front section resists twisting, and a bump stop above the final drive housing can also be used to restrict upward motion during acceleration. On front-wheel drive vehicles, a simple beam axle can be used on the rear with coil spring suspension and control arms for location. This is called a dead axle, since it only supports the vehicle and doesn't transmit any drive. It is also non-independent, as deflection of a wheel on one side of the vehicle will be transferred to the other wheel. This can be reduced by using a U-shaped axle beam with a torsion bar mounted inside it. Trailing arms are welded to the beam to locate the axle longitudinally. A lateral rod prevents lateral movement when cornering, and coil springs provide for suspension. The torsion bar is connected between the left and right wheel units, and deflection of the wheel on one side causes the axle and its torsion bar to twist together. Passenger cars no longer use beam axle front suspension, but it is still common on heavy commercial vehicles and some four-wheel drives. Trucks use an I-beam, in most cases located by leaf springs. Four-wheel drives with rigid axles may use leaf springs for front and rear suspension. Coil springs may also be used for front and rear. And as with other beam axle designs, a lateral rod and control arms must be used for location. This section examines independent suspension. One of the main benefits claimed for independent suspension is that unsprung mass can be kept low. Also, if a wheel on one side hits a road irregularity, it won't upset the wheel on the other side on the same axle. And it allows wheel camber to be adjusted individually when provided for by the manufacturer. One of the simplest and most common independent suspension systems is the McPherson strut type. It can be used on the front and rear of the vehicle. It consists of a spring and shock absorber unit called a strut. The lower end of the strut is located by a ball joint fitted to the end of the suspension control arm. Its upper end is located in a molded rubber mounting. If the unit is on the front, the upper mounting includes a bearing to allow the complete strut to rotate with the steering. A tension rod or stay bar extends from the body subframe to the outer end of the control arm. This maintains the location of the control arm during braking and accelerating. In this front-wheel drive suspension, the control arm is a wishbone shape with two widely spaced mounting points. This prevents backward and forward movement, so a tension rod is not needed. Wishbones can also be used in a parallel link system. They can be used in pairs with the coil spring between the lower wishbone and the suspension crossmember. Alternatively, the upper link may be a wishbone with a coil spring mounted above, combined with a single pivot lower link located by a tension rod. On some vehicles, a torsion bar provides the springing medium. The torsion bar is attached at the inner fulcrum point of the wishbone or control arm. As the suspension is deflected, it twists around its center. It can be fitted to the upper or the lower link depending on the type of vehicle. The upper link is shorter than the lower one, irrespective of the springing method used. When the suspension is deflected, the unequal lengths allow the track of the vehicle to be maintained near constant, but with some changes to camber angle. Generally, when the car leans during cornering, the inner wheel leans outwards at the top, and the outer wheel leans inwards. This helps to maintain maximum tyre contact with the road surface. The kind of independent suspension used on the rear of a vehicle depends in part on whether it's front-wheel drive or rear-wheel drive. If it is front-wheel drive, it may use a McPherson strut system at the rear, similar to the front suspension system. There is normally no steering on the rear wheels, so there is no need for the bearing in the upper mounting. On rear-wheel drive vehicles, the suspension arrangement has to allow for the external drive shafts to transfer the drive to the wheels. The final drive assembly is normally fixed to a crossmember, and since it must absorb the torque reaction, it must be secure. Drive shafts, either with conventional or constant velocity joints, transmit the drive to the wheels. When conventional universal joints are used, each drive shaft may have a splined section to accommodate changes in shaft length due to changes in wheel camber with suspension action. However, the drive shaft itself can be used as the upper link of the suspension, providing the pivot point. The splined section is unnecessary, and the shaft can be made as a one-piece. As with the front suspension, the lower link has widely spaced pivots to provide stability, and the unequal length links maintain the track nearly constant, although with deflection, some camber change does occur. In some designs, the wheel units are located at the outer ends of semi-trailing arms. The arms are attached to their cross-member pivot points by rubber bushes, and constant velocity joints are used at each end of the external drive shafts. This section examines coil springs. Coil springs are used on the front suspension of most modern light vehicles, and in many cases they have replaced leaf springs in the rear suspension. A coil spring is made from a single length of special wire, which is heated and wound on a former to produce the required shape. The load-carrying ability of the spring depends on the diameter of the wire, the overall diameter of the spring, its shape, and the spacing of the coils. And this also decides which vehicle it is suitable for. A light commercial vehicle has springs that are robust and fairly stiff. On a small passenger car, they are lighter and more flexible. The coils may be evenly spaced or of uniform pitch, or unevenly spaced. The wire can be the same thickness throughout, or it may taper towards the end of the spring. The spring itself may be cylindrical, barrel-shaped, or conical. Generally, a cylindrical spring with uniform diameter wire and uniform pitch has a constant deflection rate. Its length reduces in direct proportion to the load applied. When the pitch is varied, the deflection rate varies too. The spring is then said to have a progressive rate of deflection. Similarly for a varying wire diameter. And the shape. A spring with a progressive rate deflects readily under a light load, but increases its resistance as the load increases, which gives a softer ride. As conical and barrel-shaped springs compress, they collapse into themselves. This gives a longer suspension travel for the length of the spring than for a cylindrical spring, which gives a softer ride for light load situations and a harder ride for heavy load situations. As a cylindrical coil compresses, it can become coil-bound, which limits its travel. Coil springs can look alike but give very different load ratings, which are often color-coded for identification. They normally use rubber pads to prevent transmission of noise and vibration. This section examines leaf springs. The leaf spring is one of the oldest forms of springing. It is usually used on rear-wheel drive vehicles because of its simplicity. They are normally mounted longitudinally. Leaf springs consist of one or more flat springs made of tempered steel. A number of leaves of different length are used to form a multi-leaf spring. They are held together by a center bolt that passes through a hole in the center of each leaf. It is also used to locate the axle on the spring. The axle is then clamped to the spring by U-bolts that wrap around the axle housing and through a spring plate underneath the spring. Rebound clips are formed at intervals around the leaves. They prevent excessive flexing of the main leaf during rebound and also keep the leaves in alignment. The longest leaf, called the main leaf, is rolled at both ends to form eyes. These eyes are used to mount the spring to the frame of the vehicle. Some springs have the ends of the second leaf rolled around the eyes of the main leaf as reinforcement. This leaf is called the wrap leaf. The front of the spring is attached to a rigid spring hanger on the vehicle frame. The rear is connected to the frame by a swinging shackle, which provides a link between the spring eye and a bracket on the subframe. This swinging link is needed because as the spring flexes and flattens out under load, the distance between the spring eyes increases. Some springs have inserts between the leaves of plastic, nylon, or rubber. They act as insulators to reduce noise transfer and friction as the leaves move under load. Some older vehicles completely enclose the leaf springs in grease. The spring eyes are fitted with bushes, usually with a rubber, flexible section. But nylon and urethane bushes are also used, and sometimes bronze for heavy-duty applications. Rubber insulating pads between the spring mounting pad and the spring also act as insulators. And similarly, between the spring plate and the spring. The spring forms a flexible suspension unit that locates the axle housing longitudinally and laterally. It can sustain the torque reaction on acceleration and the braking torque during deceleration, and the driving thrust is transferred through the front half of the spring to the fixed shackle point. This section examines torsion bars. A torsion bar is a long alloy steel bar fixed rigidly to the chassis or subframe at one end and to the suspension control arm at the other. The bar is fitted to the control arm in the unloaded condition, and as the control arm is raised, the bar twists around its center, which places it under a torsional load. When the vehicle is placed on the road, with the control arm connected to the suspension assembly, the bar supports the vehicle load and twists around its center to provide the springing action. Spring rate depends on the length of the bar and its diameter. The shorter and thicker the bar, the stiffer its spring rate. Torsion bars can be used across the chassis frame on the same principle in a trailing arm suspension, or as part of the connecting link between two axle assemblies on a semi-rigid axle beam. After a lot of use, a torsion bar can sag. On many vehicles, it can be adjusted to allow for this. It is used in light vehicles as a stabilizer or anti-roll bar, connected between each side of the suspension on the front and sometimes the rear. When the vehicle is turning, centrifugal force acts on the body and tends to make it lean outwards. The anti-roll bar or stabilizer tries to use its connections to each side of the suspension to resist this roll tendency. This section examines rubber springs. Rubber is used in most suspension systems as bump and rebound stops. If the suspension reaches its limit of travel, these stops prevent direct metal-to-metal contact, which reduces jarring of the body of the vehicle. The stops can also be shaped to provide an auxiliary springing function, increasing their resistance progressively with suspension contact. Some vehicles use rubber as the main springing medium. This rubber cone is this vehicle's main suspension member. Increasing the load on the suspension causes the cone to act like a spring being deformed. When the load is removed, the rubber's elastic properties tend to return it to its original state. Rubber has a number of advantages. It doesn't need to be lubricated. It can be made into any shape as required, and it's silent during use. This section examines hydraulic shock absorbers. The most widely used hydraulic shock absorber is the direct-acting telescopic type. It can be fitted as a self-contained unit or combined with a suspension strut. The strut type uses the same principle of operation but is considerably larger. The hydraulic shock absorber provides its dampening action by transferring oil under pressure through valves which restrict the oil flow. The twin tube type is the most common. The outer tube is normally attached to the suspension member at its base, and the inner tube provides a working cylinder for a piston which is attached to a piston rod. The piston rod is connected to the frame at its outer end, and a bearing at the top of the outer tube keeps the rod in alignment as it moves in and out of the shock absorber with suspension action. A seal above the bearing prevents oil leakage and keeps out dirt and moisture. A shroud protects the rod from damage. During bumps or compression, the rod and its piston move into the shock absorber. In rebound or extension, the rod and piston move out of the shock absorber. For dampening to be effective, resistance is needed in both directions. This is provided by the oil and by disc valves attached to the piston and the base of the inner tube. Oil fills the inner tube and surrounds its outer surface to a level which allows a free space or reservoir to exist above it, between the inner and outer tubes. On bump or compression, the piston and rod move downwards in the cylinder, resulting in a small pressure drop in the chamber labelled A above the piston. At the same time, the volume of the chamber labelled B below the piston is reduced, causing a high fluid pressure. This unseats the piston intake valve, and fluid flows up through the outer passages in the piston and into chamber A. But the piston rod is also now entering A and displacing a quantity of fluid equal to its volume, so all of the oil in B cannot flow into A. The displaced fluid is forced down through a base valve and out into the reservoir, labelled C. In the rebound or extension phase, the piston and rod move upwards and the volume of chamber A is reduced. Chamber A becomes a high pressure area, and fluid flows through the extension valve in the piston into chamber B. However, the withdrawal of the piston from B greatly increases its volume, and fluid flow from A is insufficient to fill the space. Pressure in B falls below that of the reservoir, causing the base intake valve to be unseated. Fluid flows from the reservoir into chamber B, keeping the inner tube full. The valves provide control over the amount of force required to pass fluid through them at any given piston velocity. They can be made to open in stages according to fluid pressure. This allows light resistance to motion when the piston moves slowly and heavy resistance when piston velocity is high. The rapid movement of the piston, continually forcing the oil backwards and forwards through the valves, causes it to heat up as it absorbs the energy of motion of the spring and converts it into heat. The heat is transferred through the outer tube to the outside air. However, the hotter the oil becomes, the greater its tendency to aerate. Aeration occurs because of the high velocity of the oil as it passes through the small passages in the valves. If the velocity is high enough, air dissolved in the oil comes out of solution as small bubbles and forms a foam. Aerated oil has a certain amount of compressibility, so it is unable to provide the dampening force previously achieved in the non-aerated condition. The performance of the shock absorber is thus considerably reduced. This effect is called shock absorber fade. This section examines gas pressurized shock absorbers. In a hydraulic shock absorber, the oil heats up as the energy of motion of the suspension is dampened. The rapid piston movement as the vehicle moves over the road causes the hydraulic fluid to aerate. This reduces the dampening effect, and the shock absorber's performance very quickly deteriorates. This condition is called shock absorber fade. It can be reduced substantially by pressurizing the fluid with gas, usually nitrogen. In this monotube design, fluid fills the chambers above and below the piston. As the piston moves in the cylinder, valves control the movement of oil from one chamber to the other. Pressure on the oil is provided by nitrogen gas at the base of the cylinder, acting on a free-floating separation piston which separates the gas from the oil. On bump, the piston moves downwards, and the penetration of the piston rod displaces a quantity of oil equal to its volume. The separation piston is displaced accordingly, and gas pressure increases. On rebound, the piston and rod move upwards, and gas pressure reduces as the separation piston follows the movement. Pressure on the oil is maintained even when the piston and rod are at the top of their stroke. This section examines load-adjustable shock absorbers. When vehicles carry heavy loads, their suspension is compressed, causing the rear of the vehicle to be lower than normal. As a result, steering becomes lighter. The alignment of the headlights becomes too high, and the compression length of travel of the suspension over bumps is reduced, causing discomfort to passengers. To reduce these effects, a manually adjustable air spring can be incorporated into each rear shock absorber. The air spring consists of a flexible rubber cylinder which seals the outside of the upper and lower halves of the shock absorber. The shock absorber is a standard hydraulic type, providing normal dampening action. But when a heavy load is placed on the rear of the vehicle, the rubber air cylinder can be pressurized to assist the suspension springs. By changing the air pressure in the cylinder, the ride height can be adjusted, as well as the stiffness of the suspension. Compressed air in the pneumatic cylinder can absorb smaller road shocks and provide better ride characteristics than just stiff springs alone. The rubber air cylinder is connected to a filling valve by a flexible plastic hose. Air from a tire pump or a hand unit forces more air into the rubber cylinder, allowing the suspension to support more weight. The maximum air pressure setting must not be exceeded, as this can damage the shock absorber and its mounting points on the vehicle frame. When the load is removed, the extra air is released through a filling valve, which allows the suspension to return to its original settings. A minimum air pressure must be maintained in the cylinder to prevent tearing of the rubber as it collapses internally with shock absorber action. This section examines manual adjustable rate shock absorbers. Adjustable rate shock absorbers provide a means of changing the rate of dampening of the spring oscillations to suit varying road conditions or driver preference. This shock absorber has a manual external damper rate adjustment. The position of the valves in the piston can then be changed to vary the number of restrictions the oil has to pass through and to vary the force needed to open the valves. In this position, all of the orifices are open, and a small dampening effect is applied to the oil. The spring force applied to the valve is also reduced to allow the valve to open more easily. This means the oil can flow through the valves more easily, which gives a softer ride, but can also allow more rolling and pitching of the body of the vehicle. Closing some of the orifices and increasing the spring force applied to the valves makes it harder for fluid to flow through the piston. This increases the dampening effect of the shock absorber. The method of changing the position of the valve varies. On this model, it is adjusted by a spindle that reaches down inside the plunger. On this shock absorber, when it's extended to its maximum length, a pin is depressed, locking in an adjustable slide on the piston assembly. Twisting the two halves of the shock absorber changes the number of orifices and the spring force on the valves. This section examines electronic adjustable rate shock absorbers. Adjustable rate shock absorbers provide a means of changing their rate of dampening of the spring oscillations to suit road conditions. Electronic controls let the changes occur either automatically or as the driver prefers. Each shock absorber has a rotary solenoid that can alter the dampening rate by changing the number of restrictions the oil must pass through. In this position, all orifices are open. Oil can flow more easily through the passageways in the piston. Only a small dampening effect is applied to the oil. This provides a dampening force that emphasizes ride comfort when traveling at low speeds. Closing some orifices makes it harder for fluid to flow through the piston. This increases the dampening effect of the shock absorber, providing a firmer ride, more suitable for higher speeds and faster cornering. The solenoid is operated by an electrical signal from the electronic control unit, or ECU. The ECU allows different modes of operation according to a selector switch on the dashboard. In the auto position, the dampening effect at the front wheels is increased at road speeds above 80 km per hour. This improves vehicle stability at high speeds. The rear shock absorbers stay at their normal setting. The manual position has two settings, normal or sport. In normal setting, all shock absorbers remain at a rate suited to ride comfort. There is no change to the settings at high speeds. The sport setting increases the dampening rate of all the shock absorbers. This is more suited to brisk driving with heavy acceleration and cornering. This section examines automatic load-adjustable shock absorbers. They are also called self-leveling. When vehicles carry heavy loads, their suspension is compressed, causing the rear of the vehicle to be lower than normal. As a result, steering becomes lighter. The alignment of the headlights becomes too high, and the compression length of travel of the suspension over bumps is reduced, causing discomfort to passengers. A lower vehicle handles better on smooth roads, but on a rough road, reduced suspension travel can let harsh road shocks be transmitted to the passenger compartment and cause discomfort. An automatic load-adjustable suspension system controls the vehicle ride height automatically, according to the load placed over the rear axle. It consists of air-adjustable shock absorbers fitted to the rear suspension, an electrically driven compressor and air dryer assembly, and an electronic control unit, and associated wiring and tubing. The ECU is mounted to the cross member over the rear axle, and a movable link connects it to a rear suspension member. As the vehicle is loaded, the normal suspension springs are compressed, which lowers the height of the vehicle. When the ignition is switched on, the ECU senses the lowered ride height and switches on the air compressor. Air is directed to the shock absorbers, causing the airbag around them to expand and raise the suspension to the normal trim height. If the load is removed, the suspension springs expand, raising the height of the vehicle. The ECU senses the raised ride height, and air is exhausted from the shock absorbers, causing the airbag to deflate and lower the suspension to the normal trim height. During normal suspension operation, continual adjustment of vehicle ride height is prevented by a time delay in the ECU. This allows the trim height to be adjusted only when the ECU reads an out-of-trim signal for 5 to 15 seconds. The compressor run time or exhaust time is limited to 2 minutes. This prevents it continuing to operate if the system develops an air leak or if an exhaust vent remains open.